This is lecture number 6. In this lecture, we're going to have an overview of the ATMEGA328P microcontroller. The ATMEGA328P is the microcontroller used in the Arduino Uno. This is a block diagram that shows all the various connections on an Arduino chip. An Arduino Uno processor. And so you can see there's a whole lot of stuff going on here. Up here we actually have the pinout for the ATMEGA328. Once it's embedded into this Uno, you have a different set of pinouts, and so here are all the pinouts. Notice that some of these are for the R3, Arduino Uno R3. So that is a little bit different than the Arduino Uno R2 and the original Uno and the 2009 Arduino, sometimes called the 2009. So those are all very similar, but the R3 added some things. So this is the legend that explains what the different colors mean on this diagram. So in this diagram, we have a lot of information going on. And the sooner you learn all of this information, the better. So some of it is going to come by use. Some of it is just going to come by staring at a diagram like this and just absorbing it. When you look at this stuff, it seems all very cryptic. It seems all very overwhelming because there's a lot of stuff going on. But I recommend that you take a good look at this diagram and refer to it often. This diagram is the main diagram for all that we're going to be doing. So it shows not only the processor itself, but it also shows us the Arduino Uno. So a lot of stuff going on. So with the power jack, for example, it shows what's going on. Here, these various connections. These connections are important to understand what's going on with them. So each of the connections has a number associated with it, and each of the pins has multiple applications. So this is very important to understand. Each pin can be used for a number of different applications. So obviously it can only be used at one application at a time, but it is very versatile in that it has a lot of things it can be used for. So this diagram shows, for example, which pins are the pulse width modulation pins. It shows what the PC interrupt number is for each one of these pins. So PC int is the each of the pins can be used as an interrupt pin. All of the input-output pins can be used as interrupt pins. There are two that are specifically defined. So those are int 0 and int 1 are specially defined. Okay, those have a special hardware connection. Otherwise, any of the other pins can be used as PC interrupts. So when we get to talking about interrupts, we'll see what the PC interrupt, the pin change interrupt, what that's all about. Okay, the yellow shows what port those pins are connected to. There are 3 I/O ports, a B, C, and D. There's no port A, and we'll see some of that as we go on. These pinks show the digital pins. So here they're called IDE, but it's really, these are the digital pins that we have. The green indicates analog, what's going on with analog. Okay, so notice that these pins, these analog pins, are both analog pins and digital pins. So this is digital pin 14, 15, 16, 17, 18, and 19. So if we use them as digital pins, those are the numbers. Otherwise, we can use them as analog out, analog 0, analog 1, and so forth. So we have that situation. again, there are multiple uses for a lot of these pins. Some functions appear in more than one pin. For example, SCL and SDA appear on these pins, but they also appear over here. These pins over here are actually mirrored over here. And so we have a number of pins that on the Arduino are mirrored to multiple locations. Okay, so these guys, for example, are mirrored. These pins here, the guys from this ICSP connector, are mirrored, and so you can see which ones they're repeated from up above. Let's look a little closer to some of these. So on the left side of the Arduino, we have these pins. This first pin on the Arduino R3 is not connected to anything, which is kind of weird, but they wanted to use a standard 8-pin connector over here. Okay, I/O ref. We'll talk a little bit about that. Let's see. So here's a reset, the reset button or pin. We can apply a voltage to that to reset our Arduino. This provides our 3.3 volts. That comes, there's an onboard voltage regulator that will supply that voltage from the USB bus, or from powered from the USB bus or from the barrel jack. It will generate that 3.3 volts that we can use for projects. There's a 5-volt connection that we can use. There are 2 ground pins that we can use, and then there's a VN pin, and we'll talk about that another time. So basically, it's input voltage to the Arduino when it's running from external power. So anyway, we have that. We have these analog pins, and again, we can use them as interrupts, pin change interrupts. Otherwise, these are port C pins. So when we come to talking about the different ports, these are port C pins. Overall, these are the pin numbers for the Arduino. These numbers don't have a whole lot of significance. These are analog channels, or if we use them in the Arduino IDE, these are the analog channels that we would use for them. Otherwise, as digital channels, these are their numbers. Again, they can be used as pin change interrupts. When you if you include a certain header, these pins have these predefined names, and again, SDA and SCL is used for I2C communication. So these 2 pins are used for I2C communication. So those are these sides of the Uno. On the right side of the Uno, we have these pins. Okay, so again, we have these. So port D. So you can see here are the port D. These are all the port D pins. They're all right there. Here are the port B pins. Some of the port B. Notice there are a couple of port C pins here. And in terms of digital pins, these are the digital pins that we have. These are the numbers for them. There's a ground pin over here. Analog reference. That's used for the analog digital conversion if we choose to use it. It has these alternate uses. So notice it has this TXD and RXD here. These are actually the, so transmit and receive, that's actually the serial communication link that's used when the Arduino is being programmed. Okay, and so they can also be used for other things, but that's a particular application that they have. Okay, so T1, int1, those are interrupts. T1, T0, those are for clocks. Analog in 1, analog in 0. We'll talk. As we go along, we'll see what those are for. Clock 0 is 1 clock, and then we have these. These are other connections for various clock purposes. Okay, so these are also used for clocks or timers and counters. So that's what those are for. So notice over here I have Meso and Mosi, and slave select here, and clock. So these pins are used for SPI communication. Okay, so so notice here I have OC1A and B, OC2A, OC0A. So here's the other, and here's OC2B. Okay, so we have those different. These are all again associated with timers and counters, and so all of the pins have, as you can see, multiple purposes. And so part of learning the Arduino in its full detail is learning all the multiple purposes, what all the purposes for the Arduino are. So as we go through this overview, we're going to see all of these different things going on. And again, so the first unit, when we came into this, we came at a very top level, very high level, okay? And we were only seeing the like very basic functionality of the Arduino. Now, as we get in a little deeper, we're actually seeing there's a whole lot of stuff that's happening here, stuff that you weren't seeing in the standard Arduino IDE. And so here we're going to get a little deeper into this. Okay, we're getting deeper and deeper. This is an overview of all the internal components inside the ATMEGA328. Okay, this is all the stuff. These are all the major guts parts of our Arduino. So this is the ATMEGA anatomy. So this is your anatomy diagram. It would be helpful basically to memorize this diagram. This is one of those few things that we're really going to encourage you to memorize, and not necessarily. I mean, if you can memorize it. Some people are really good at being able to see a picture and just get all the details and all that. If you can do that, that's great. Otherwise, just remember what everything. First of all, know what everything on the diagram is. Second of all, if you can kind of remember how they interconnect, that's very important. Okay, so let's take a look at this. We're gonna take some time and actually look in detail at all of these things as we go along. But it's helpful to have this as an overview. This, if you have a grasp of this diagram, it will save you a lot of headaches, a lot of misunderstandings as we go along. Okay. So over here we have power and ground. That's good. It goes into this block, which is basically something that provides power for the entire system. Even though it doesn't actually show any outputs, really this provides power for the whole system. But there are a couple of inputs to it. One is something called a watchdog timer, and the other is something that comes from port C all the way over here, and that's basically the reset. Okay, you have a couple of different sources that can reset your Arduino. Okay, and obviously, if you shut down the power, that's going to shut it down. If you power it up, then that will be like resetting it. But there are other resets. So what's this watchdog time? What is the dog about? What's the dog doing? Who let the dogs out? No, it's not that. The watchdog is it's basically the idea of it's possible for your system to get into a condition where it gets locked up and it's not doing anything. It's not doing what it's, first of all, it's not doing what it's supposed to do. Second of all, it's kind of in a limbo state. That can happen. And it can happen for a number of reasons. Sometimes it's caused by a bad program. Sometimes it's caused by, so a bad program meaning, for example, if you have an interrupt system structure, and the interrupt service routine takes too long, and you get another interrupt, and so it goes to do that routine, and then you get another interrupt, and you get a long string of interrupts. You can, it just kind of, the processor just kind of gets piled up on top of itself, and okay, so that's a bad thing, and you certainly want to avoid that when you do programming. But there are things like that. Even a good program can still have situations where it locks up. Now, the simple programs you've been working with, for the most part, are not going to give you any problems like that. But it's not. It's when you start doing things more complicated, you want the ability to have a watchdog timer. The other thing that can happen is if you get like maybe a voltage spike or some EMI or something, it can send your system into a state that is uncertain, unknown, unpredictable, and unusable. So the watchdog timer basically is used to wake the system up. Okay? It's used to, in other words, to wake the system up, or in other words, reset it. So associated with the watchdog timer is a watchdog oscillator that basically is used to keep track of that. So if you think of what a timer is, a timer has some kind of a timing source, which is usually like a clock, an oscillator. An oscillator basically is a clock. It switches back and forth at a regular interval. And so basically, the watchdog timer can be set so that if nothing happens for a certain period of time, it will reset the processor. So in other words, if it gets locked into some condition, it will reset after a certain amount of time. So that's what the watchdog timer is all about. Okay, I've talked way more than that than I intended to, but anyway. So in general, there are a number of oscillator circuits and clock generators. Okay, so the orange refers to timing and counting functions. So these are the oscillators, and we'll see a diagram of these circuits in a little bit. Then we have these counters. We have 3 counters, 0, 1, and 2. 2 of these counters are 8-bit counters. One of these counters is a 16-bit counter. So T/C refers to timer counter. Okay, so basically, a timer is something that counts clock pulses, but it counts, right? So a timer is actually a counter. It uses a counter to keep track of the time, whereas a counter is just a counter. So a counter will count pulses, but those pulses don't have to be like periodically spaced. They can just be, whatever events are occurring, and it's just keeping track of the number of those events. So timers and counters can be used. So 2 8-bit timer counters, 1 16-bit timer counter. So these have various advantages for which they are used. So if we notice, timer 0 is connected to port D, okay, and timer 1 is connected to port D and B. Timer 2 is connected to port B, okay. So these ports are where a lot of the interconnections happen. Okay, so those ports are really important. Okay. There's a data bus that connects all the major components. So here's the CPU for the system, and it's connected to the data bus. And a lot of other things are connected. So for example, I have 3 different kinds of memory. I have static RAM, flash memory, and EEPROM. So electrically erasable, programmable, read-only memory. So when you write stuff into the EEPROM, when you shut the power off, it stays there. Okay, so that's one of the values of EEPROM, is it's non-volatile. Also, flash memory is non-volatile. The static RAM is volatile, which means when you power it down, whatever's in there either goes away or gets corrupted or whatever. So that's important. We'll talk more about what happens inside the CPU. So there's actually a lot of stuff in some of these components like this and like this. Okay, so here I have these guys here. These are our serial communication links. So there's a universal synchronous asynchronous receiver transmitter that the system has, and that's connected to port D. Our SPI communication is connected to port B. This is port D, port B, and our 2-wire or I2C communication is connected to port C. So each of the ports has its own serial communication. So you can have 3 different kinds of communication going on simultaneously by the way they're connected. Okay, so notice that that port C itself, well, anyway, yeah. So port C, these blocks are analog to digital related blocks. So we have an analog comparator that's available. We have a band gap, and we have the actual A to D converter. So it turns out there's only, and we'll see some of this in greater detail as we look further into the ATMEGA. But so in a number of these blocks, we have sub-blocks within them that provide more detail. So our actual ports, we have an analog to digital port comes out. Notice that there are actually 2 bits that come out. We have a crystal, which is our clocks that come out. We have port C, port B. Notice that port C only has 7 bits. Port B has 8 bits. Port D has 8 bits. Okay, so those are important to keep in mind. All right, so this is the overview of our of the guts of our Arduino processor, the ATMEGA328. Okay, so here are some of the features. As you can see, there are a lot of features of the ATMEGA328. I don't want to read all of this to you, but just to let you know some of what's going on here. This is important. So this is all useful stuff, and at some point you're going to learn everything in here. Okay, you're going to know all of this stuff. It seems like a lot of stuff right now, and it is, but it's not that. Once you work with it for a little while, it's not that difficult. So we have this is our controller. It's a high performance, low power 8-bit microcontroller. So if we went to a 16-bit or 32-bit microcontroller, we could actually do things more efficiently. But again, we've talked about the different purposes for different microcontrollers. It uses a RISC architecture, reduced instruction set. Okay, reduced instruction set controller. So basically, this is what we have about the reduced. So reduced. So for a while there, they were making processors that were called complex instruction set, which means they had some built-in functions that were fairly complex. Okay, so a reduced instruction set architecture basically reduces the number of instructions, which means that you have, if you want to do a complex thing, you have to use several instructions to make that happen. So that's important to understand. We have different kinds of memory available. So static RAM, EEPROM, flash, and so forth. So that's the memory. So we have some power features of the, some important features of the Arduino. Here are the peripheral features. We'll talk more about those. I/O lines. Okay, so a lot of this stuff we've looked at in some detail already. Once again, here is our ATMEGA328 pinout diagram. Okay, and again, here's the legend for this diagram. So again, it would behoove you to remember all of this information. And actually, a lot of this information is available in Appendix A in the book, in the textbook. Okay, so on the chip we have ports B, C, and D, and here are where the pins come out on that chip, on the ATMEGA chip. Okay, so we saw ports D, B, and C coming out. Okay, these are bidirectional ports, which means the data can go both ways. They can be input ports or output ports. Okay, so let's talk a little bit about the RISC processor, reduced instruction set computer, as compared to a complex instruction set computer like the Pentium and so forth. The philosophy behind a reduced instruction set is that simpler instructions execute faster. If you have fewer instructions to work with, then they execute faster because you don't have to figure out what's going on with the different instructions. And so as a result, it's optimized so that especially the most used instructions are optimized. There are other RISC machines available out there, and these became popular in the 1990s. Here's what the internal processor layout for the ATMEGA looks like. So this is in that overall block diagram, this is the CPU that we saw. This is the inside of the CPU. Okay, so and it's part of the inside. So here's our data bus, and inside of the CPU, this is the stuff that's mainly inside. EEPROM is not there. The data RAM is actually part of that. The watchdog timer, again, is separate, as are the I/O modules. So what's really significant in the CPU is you have, first of all, program memory with instruction registers and instruction decoders. Those go to control lines. The data bus also connects to the program counter that affects the program memory. You have status and control registers. You have general purpose registers. Those feed into our arithmetic logic unit. Okay, and so you have direct addressing and you have indirect addressing that can happen. Okay, so this is basically an overview of all that. So notice that the arithmetic logic unit may take two things from the registers and put out one thing. So for example, I can add two things and get something out, or subtract two things, compare two things, and so forth. So there are 32 8-bit registers. These are mapped to address space 0 to 31. Most instructions can access any register in one and complete in one cycle. Of the 32 registers, the last 3 register pairs, that is the last 6 registers, can be used as 16-bit index registers. And we'll talk, when we get into, we don't need to really know that so much right now, but when we get into the assembly language portion, we're going to need to use those things. There is also a 32-bit stack pointer. Okay, we'll talk, again, the stack is something that's kind of invisible to you until you actually get into the assembly language program, and then it's really important. Flash memory is a non-volatile program space storage, 16-bit wide. Some devices have a separate lockable boot section. What that means is you can write stuff to the boot section. The boot section is what gets read when the system resets. Okay, and so at least 10,000 write and erase cycles. So it's non-volatile memory, and because of that, it's limited in the number of writes and erases. Okay, so 10,000. So basically, are you going to program your Arduino 10,000 times? Really? That's a lot. I mean, if you program it 100 times, you're probably doing more than the average user is going to do. So, okay. Here's what the SRAM, static RAM, looks like. The static RAM has 32 registers, 64 I/O registers, 160 external I/O registers, and then the rest of the internal static RAM. Okay, and the amount of internal static RAM depends upon which Arduino you're working with. Okay, so the ones we're going to be working with have 2048. And then you can add external RAM, SRAM, to the system. Okay, but internally, the 328 has its own static RAM built in. Okay, so EEPROM, electrically erasable, programmable read-only memory, requires a special write sequence. So when you write to it, that's part of this programmable. Okay, so it's non-volatile storage for program-specific data, for constants, etc. So if you had a bunch of data that you wanted to put into memory, and you're always going to work with that data there, EEPROM may be a good way to go for that. So notice that it has at least 100,000 write and erase cycles. So it's definitely more versatile in that way than the flash, but it's more complicated write sequence. So and erase sequence. Okay, memory mapped I/O space. So the I/O registers input are basically visible in the data space. So in other words, there's nothing special about them in terms of how to access them. The I/O can be accessed using the same kind of instructions as accessing data. So if you're putting something in RAM, it's the same kind of instruction as putting something out to a port or reading something in from a port. The compilers can treat the I/O space as data access. So that's part of the memory mapped I/O. There are also specific bit manipulation instructions. So if you want to set or clear a single I/O bit, you can do that. Notice that this only works on lower memory addresses. So it's limited, but on certain of these, you can do that. The arithmetic logic unit. It's directly connected to all 38 general purpose registers. So we saw those registers and how they feed into the ALU. Well, we can connect any of the 32 registers to. So in other words, I can add register 1 to register 17, or any combination of those things. So operations between registers are executed in a single clock cycle. So you can also access data from other places like EEPROM or whatever, but it takes longer if you're going to do that. It's going to take longer than a single clock cycle to do something like that. The ALU supports arithmetic, logic, and bit functions. And there is a multiplier on chip, and it takes 2 cycles. So most operations execute within a single clock cycle. The multiplier takes 2 cycles. And there isn't a divider per se. Okay, there isn't a divider per se, but there is something like a divider that we can work with, the mod function. But okay, in terms of the RISC instruction, there are 131 instructions altogether. Okay, and it would be a good idea to memorize them, but I'm not going to ask you to do that yet. Well, actually, I'm never going to ask you to do that. You will always have access to the resources for all of those instructions. Most of these instructions are invisible to you. Okay, they have been invisible to you up until this point, right? So even when we program in C, we still won't see this. Where we will see these instructions is when we start to program in assembly language. Then we'll see all of those. We'll need to have access to all of those instructions. Okay. For now, the C compiler or the Arduino IDE compiler compiles it into these kinds of instructions. So if you have a floating point multiply, it does all the work needed in order to do that multiplication. Okay. Converts from floating point, it does all of that stuff. And so it's been transparent to us. But when you get into assembly language programming, it's no longer transparent. You have to make everything happen. Okay, so there are arithmetic and logic instructions. There are branch instructions. So that's the kind of thing where if this number is bigger than this, then go here, and so forth. There are bit set functions, clear functions, and test functions. So set and clear. Set means that you make the bit 1. Clear means you make it 0. And test is to see whether it's a 1 or a 0. Data transfer. I can transfer from one register to a port, or port to a register, or whatever. And then there's the microcontroller control. Those are all the types of instructions available. Here's some information about instruction timing. Again, we're not going to go into a lot of the details of this yet. We'll see more of this when we come to the assembly language portion. But you can see many of the things require 1 or 2 cycles. So if I want to take data from one register to another, it takes 1 cycle. If I want to go from register to memory, it takes 2 cycles. If I want to branch, that is, if I want to jump in instructions, then that's 1 to 2 cycles. A subroutine call can take 3 to 5 cycles, and so forth. Okay, clock system. The clock control module generates clocks for memory and I/O devices. There are multiple internal clock sources. Provisions for an external crystal clock source with a maximum 220 megahertz. So the Arduino system uses the ATMEGA328. The Arduino system has a crystal clock source that's 16 megahertz, so that's less than 20 megahertz. And so the ATMEGA makes provision for that. Internally, there is an 8 megahertz RC oscillator with a divide by 8 prescale that yields a 1 megahertz CPU clock. So if you do not supply an external crystal oscillator, it will use its own internal 1 megahertz clock. So 16 megahertz, 1 megahertz, definitely a lot slower if you do not supply a clock. Fortunately, the Arduino does supply a clock, so we're good. So this clock also is not very accurate. It's only 5 to 10% accurate. It's not that accurate. So you can use, there is internally a clock, but you probably don't want to use it. Okay, so here are the clock sources available. So there's a timer counter oscillator, there's a crystal oscillator, there's an external clock that you can bring in from another source. There is a low frequency crystal oscillator, and then there's the calibrated RC crystal RC oscillator. These go into a multiplexer, and so the actual clock that's used is chosen from this multiplexer, and it's chosen from among these. Okay, and then there's a system clock prescaler that basically divides whatever clock here by 8, and so that gives us the overall clock control. So the reason for this division by 8 is because it that actually makes the whole clock system much more accurate if we can do that. It's not to slow everything down so much. So timer counter oscillator goes into this clock control circuit that controls the timers and counters. It also controls timing associated with the I/O modules, so that's what uses to latch the data in the I/O modules. It also is used for the analog to digital converter. It's used for the CPU core, for the RAM, and flash and EEPROM. So notice that in a controller, microcontroller, microprocessor, any of things, all of those things rely upon a synchronous clock source. And so this is what provides the clock source. Okay, so that's what we have. Power management. There are multiple power down modes. Okay, there's the ordinary power down modes. There is a wake on a reset, external reset or watchdog reset. Okay, then there's a power save mode that will wake whenever there's a timer event. And there are several standby modes. Okay, so unused modules can be shut down that way. There are a number of reset sources. There's a power on reset. So as soon as you power on, that resets the whole system. There's an external pin that can be used to reset the system. There's a watchdog system reset, and then there's what's called a brownout detect reset. So this is where a brownout is when the voltage level on the processor drops below a certain level, so that when it drops below that, then the system no longer reliably is functioning. So you can get all kinds of weird, unpredictable behavior if the voltage drops below a certain level. And so in that situation, there's a brownout detect function that will reset the system. Interrupts. The ATMEGA328 has 26 reset interrupt sources. That's a lot. You can have 26 different things interrupting. And so it's like, why so many? Why so many? You will never use all 26 interrupt sources. If you do, then you can't do anything else. So basically, every input and output pin has a reset capability. Okay, and so the reason for that is because if you're using, for example, if you need a pulse width modulation, well, you have 6 pins that can do pulse width modulation. Well, that takes those out of commission if you want to do interrupts. If you want to do other communications, like TWI or SPI or I2C communication, that takes those pins away. You can't use those. And so it's not hard, again, because these pins are have multiple functions, it's not hard to run out of pins to do stuff with. And so this basically makes it so that pretty much whatever you're doing, if you have any spare pins, you're going to be able to use some of those as reset pins. Okay, so there's one reset source that can be used as an interrupt. There are two external interrupt sources. Okay, so these are specifically defined pins that can be used for externally for interrupts. Otherwise, all 24 general purpose input-output pins can be used as pin state change interrupts. Okay, so these are often used for peripheral device events. So interrupts are available, and they're quite popular on the Arduino. Interrupt vectors. Each vector is a 2-word jump instruction. The vectors start at program memory address 0. The reset vector is at address 0. So when the Arduino resets, the program counter starts at address 0, and it will jump to a subroutine that is specified at that address. So this address specifies where the boot code basically lies. Okay, so after that we have the different interrupts. So here's the external interrupt 0, external interrupt 1. Okay, and so these tell the Arduino where to go in the event of that. So so this is actually written in assembly language, and we'll come back later when we talk about assembly language and how all of this comes to pass. But so this is a jump to the placing code with the label of reset. This is jump to the placing code in the code with this label. Okay, external interrupt 0, and so forth, so forth. So this is what's called the interrupt vector table. The system, the ATMEGA, has onboard fuses. Okay, so there are fuse registers and so forth. I'm not going to talk. So here are here's some information about those fuses. Okay, I have never used them, so I don't have much to say about them. But the only important thing is, if you're going to use fuses, it's possible for you to what they call bricking your ATMEGA by working with the fuses, and you can put it into some configurations that make the system unusable. So that's all I'm going to say about fuses. Peripherals. These are the things that are already connected up to your CPU. There are 23 general purpose I/O bits. There are 3 counters, 2 8-bit counters and 1 16-bit counters. There's a real-time counter with a separate oscillator. There are 6 pulse width modulation channels. There are 6 or 8 analog to digital converter channels. Depends on the package. Okay, so the ATMEGA328 actually has 8, of which only 6 are usable. There's a serial, universal synchronous, asynchronous receiver transmitter. There are interfaces for SPI and I2C or TWI. TWI stands for two-wire interface, and that's basically the same as I2C communication. There's an analog comparator and a programmable watchdog timer. So these are some peripherals that are built in to your ATMEGA. Our general purpose input-output ports, there are 3 8-bit I/O ports. Okay, 3 8. So these are the 3 ports: port B, port C, and port D. Okay, the pins are identified as PBX. So the X here stands for pin 1, pin 2, and so forth. Pin 0. Okay, So PBX is referring to some pin number, PCX, PDX, and so forth. So the I/O ports go to these ports, ports B, C, and D. There is no port A, and each pin is configured as, it can be configured in one of four ways. It can be configured as an input with internal pull-up, as an input without internal pull-up. It can be configured as output low or output high. Okay, output low or output high. So this is these are the four configurations that you can put any pin into. So recall that when we have a in this configuration, this is often referred to as the high Z configuration. When you have it in that configuration, there is a high input impedance on that pin. Again, every port pin has alternate functions, and we saw that when we looked at those diagrams. Internal peripherals use some of the alternate functions. So, for example, in your Arduino programs, you use the command. You may have used the command delay. So, for example, in the basic blink program, you have a delay. Well, that delay actually uses a timer, and by using a timer, it's taking up pins. Okay, that can't be used for something else. All right, so it's important to understand that when you do something, certain things use certain pins, and when you use those pins, then you can't use those pins for something else. And it's important to understand what you can do and what you can't do. Okay, so the internal peripherals use the alternate functions, and each port pin can only be assigned one function at a time. Okay, so again, here are the different functions that we have. So for example, pin 5 can be used as a system clock or PC interrupt 5. Okay, but I can't use it as both. So if I want to use SPI communication, I cannot use pin 5. If I want to do SPI communication, I can't use, PB5, port B5. So all of these, again, are described in Appendix A. So this kind of thing, Appendix A in your textbook. Timers and counters. There are 2 with 8-bit registers, 1 with the 16-bit registers. Basically, these increment or decrement on every clock cycle or every input to the counter. These registers can be read on the data bus. The output feeds a waveform generator. Okay, so this is important. This waveform generator is important. We're gonna look at that quite a bit at various times. Clock sources. Again, we saw the clock sources internal from the clock prescaler, or you can supply an external clock source. And again, if you do that, it uses one of the port pins. There are multiple operating modes for these timers and counters. You can use it as a simple timer or counter. You can use an output compare function. Okay, so the output compare function can be used if you want, for example, instead of counting all the way, for example, all 8 bits, suppose you only want to count up to 6 bits. Okay, when it's gone all the way through 6 bits, then it resets back to 0 or whatever. Okay, so you can have it count up to, so 8 bits means you can get 0 to 255. So if you wanted to count up from 0 to 127 or 131 or whatever, it'll count up to 131 and reset. So that's the idea of an output compare function. That gives us a waveform generator. So when we say waveform generator in this context, they're always pretty much triangle waves. In other words, the register counts up to a certain value and then it resets. Okay, or you can have it count up and then count down and then count up. But again, they're like triangle functions. It goes up and then down, up and then down, or it goes up and then down like that. So that's the only kind of waveforms that we're really talking about. So it's not like we're making like a signal generator where you can get sine and cosine, all those kinds of functions. This is triangle waves. So you can, as this thing is counting, and when the count reaches a certain value, you can either have it set, you can have it either clear, which means it goes back to 0. You can have it set, which means it goes all the way up, or it can toggle. So those are some of the things. We'll talk more about that when we talk more specifically about the timers and how they work. You can adjust the frequency to some extent, and then you can also use the timers and counters are also used for pulse width modulation. Okay, and we'll talk about how pulse width modulation works in general. This is the overall block diagram for each of the timer counters. Okay, this is the overall block diagram. So so notice we can have an external clock that comes in, and we have these different registers: TCC, R, and A, TCC, R, and B, OCR and A, OCR output control register, timer counter control register. Okay, so we have these different registers. So notice OCR and A is not the same as OCNA, and so forth. OCNB. Okay, so this is what the overall block diagram for this looks like. And so here, in this case, N is which of the timer counter you're talking about. So N could be 0, 1, or 2. Timer counter 0, timer counter 1, timer counter 2. So here is an example where we have it specified for timer counter 0. Okay, so this is, and I'll have a similar diagram for timer 1 and timer 2. Okay, so that's the kind of thing we're talking about. So notice that there's automatically a comparison, and if you choose, you can send that to an interrupt request. So this can generate an interrupt. Each of the timers can generate an interrupt, and with each timer there are actually 2 timers. Okay, there's a timer A and there's a timer B, and so that's where that's where these come from. So even though you only have 3 timer counters, each of those in a sense have 2, but they're not completely independent. Okay, they're a little bit different, but they're not completely independent. So the basic clock is the same for both of them, but what they do with that clock can be different. Okay, so output compare register. Okay, so that when that clock is just going to clock, right? So that's going to do something, and it depends on what's in this register and how it compares as to what's going to happen out here. Okay, so to kind of see what's going on with that, to control the frequency of a clock, we can use, for example, clear timer on compare match. Okay, so OCN, so N again is 0, 1, or 2, depends on which timer counter you're talking about. And this will toggle on compare match. Okay, so basically, in this case, it counts all the way. So even though it shows a line like this is actually, it's taking a clock source and it's counting. Okay, so you can see that as it counts, this is just going up. So what you don't see here is the timing for the individual internal clock sources that are making this go up, but that's what's happening. It's going from 0 all the way to the top value. So this top value is what appears in that register. So if we have this value in that register, then this will count, and when I get all the way, when this count gets up to that value and it compares, it says, there's a compare match, and so then it'll go down to 0. Okay, so a toggle means, okay, so I'm up here. When it reaches there, it toggles, which means it was high and now it's low. Okay, it goes up again. When it hits here, it toggles. So it was low, now it's high. It goes up to here and it toggles, and so that it was high and now it's low. Okay, and then I change the value, and now it goes to a different value, and when it gets to that value, it toggles, and so forth. So this is one way of controlling the frequency of a to generate a signal with a frequency that you can determine. Okay, so if this value were like 1, then basically this clock would toggle every clock cycle. Okay, if this value here were down at 2, it would go 2 and then reset, go 2 and then reset, and so forth. And so I can get these pulses to be anywhere from 1 clock cycle all the way up to 255 clock cycles. And I can have any value in there in between. So the smallest clock cycle I can get is the base clock, but otherwise I can get any multiple, any integer multiple of that clock cycle. Okay, so this is how we control the frequency of a clock. Okay, pulse width modulation. Basically, we've seen pulse width modulation. It's dynamically changing the duty cycle of a waveform. So the pulse width modulation is set up to a certain period, which is 500 hertz, and so 500 hertz is basically 2 milliseconds. Okay, and so that's the period. And so the duty cycle then is related to the period. Okay, and so depending on the duty, so this is 50% duty cycle for this period. Here we have like 10% duty cycle. Here we have like 80% duty cycle. Okay, so fast pulse width modulation mode. The counter counts from bottom, which is 0, to some max value. The counter resets to 0 at max. And then the comparer clears at the top and it sets at the bottom. Okay, so that's basically what happens for fast pulse width modulation mode. Let's see what that looks like in terms of the signals that are going on here. Okay, so we start at the bottom, and there are two things happening. So there's the compare value. So this is the compare value for the pulse width modulation. So when the compare value is here, I'll get one pulse width modulation duty cycle. When it's here, I'll get a different pulse width modulation duty cycle. Okay, so this just shows a change from one duty cycle to another duty cycle. Okay, so notice this wave is the same regardless of what duty cycle. Okay, and what you see here is whenever it gets to the top, that's when it sets. Okay, that's when it sets. So after it's set, it goes up, and whenever it hits the compare value, then it clears. Okay, and it stays cleared until the next set. Okay, it stays cleared until the next set. So the larger this value is, the larger the time on is. So notice the time in between purples here is the same, regardless of what this value is. So that it's always going to set when this transition occurs. Okay, so it sets on the bottom, clears on the. So this is the max value. This is the top value. Okay, so it's important to keep in mind you have a bottom, a top, and a max. Sometimes the max is the top, sometimes not. In this case, it's going to set on the bottom, which means it goes to 1 when it hits down here. It's going to clear on the top. So when it gets to here, it's going to clear. That means it goes to 0. Okay, so when it gets to the max, that's when the timer just starts over again. So we have those three things going on in this pulse width modulation. So at first, when you first look at this, it's like, what in the world is going on? And again, this is the kind of thing you just kind of have to look at it. You have to work with it to fully understand what's going on. Again, we're going to look more in depth, more in detail about the timers and the counters. And so hopefully you'll be able to get a better grasp of what's going on. But this is a very simple, nice, simple illustration of what's going on with the pulse width modulation. There are a number of pulse width modulation types that we can work with. Okay. So timer 1 capture mode is something that can also be used, and this is basically the details behind that. I'm not going to go much into that. Okay. Okay, let's talk a little bit about the analog to digital converter. There is a 10-bit successive approximation analog to digital converter. There is an 8-channel multiplexer that uses the analog to digital converter port pins. So what this means is I have 8 possible things that I can convert from analog to digital. 8 possible things. Okay, the multiplexer means it chooses one and does the conversion. So if you want to do an analog digital conversion of, let's say, let's say I want to bring in 3 analog signals. It does not do them simultaneously. Okay, it'll convert one. So the multiplexer will pick one, it'll convert that one, it'll pick the next one, convert that one, pick the next one, convert that one. And then depending on how your program goes. So if you have those 3 commands in a sequence, that's the sequence it's going to follow, right? If you do an analog read, analog read, analog, it'll do an analog read, analog read, analog. It will not get them simultaneously, okay? Exactly simultaneously. Now, they will probably be pretty close to one another. Well, actually, the maximum conversion time is 260 microseconds. So the reason it's maximum is that for some values, if it just happens to be a convenient value, it actually can take significantly less time to do the conversion. This is the maximum time, 260 microseconds, so less than a millisecond. Actually, less than about a quarter of a millisecond. That's the maximum. So it has limitations. Okay, so that's the maximum conversion time. Analog comparator is a kind of analog to digital converter that's used. It compares voltages between pins A in 0 and A in 1. So there are 2 pins that can be brought in, the signals brought in and compared. A signal is asserted when one is greater than the other. So the AC0 can be used to trigger timer capture functions. And so rangefinders indicate distance with the pulse width. Timer capture mode can compute pulse width. So that's analog comparator. As was mentioned, the Arduino can do SPI communications, serial peripheral interface, which is an industry standard serial protocol for communication between local devices. It is a master-slave protocol and is a 3-wire interface, at least 3 wires. Okay, so I say at least. The number of wires in the communication schemes depends on how many devices there are. If there are 2 devices, it takes 3 wires. If there are 4 devices, if there are 2 devices, it takes 3 wires. If there are 3 devices, it takes 4 wires, and so forth. Okay, and we'll see why in just a minute. Basically, the slaves are addressed using a slaved select input line. So here's an example where I have 3 SPI slaves. Okay, and so notice 1, 2, 3, 4, 5, 6 lines. Okay. So notice that in order to communicate between the master and the slave, it has to have a slaved select line. So basically, this line is, notice the bar means it's active low. So when it pulls this line low, then this device knows it can communicate with this device. And so notice that we have, there's a clock for the communication. There's a master out slave in. There's a master in slave out. So you notice the arrows. master out, slave in. This is communicating that way. Master in, slave out, it's communicating that way. So you have what's called duplex communication. Communication going both ways simultaneously. Okay, so the master can be communicating with the slave while the slave is communicating with the master. So it will only communicate when the slave select line is low. So if the master wants to communicate the same thing to all the slaves at the same time, it would set all of these low at the same time and send out the same information. So it can do that. So a number of things can happen with these kinds of devices. Okay, so the SPI bus operation works this way. The master drives a particular slave select line. Okay, the clock signals the device and sets the master out, slave in, master in, slave out, the MOSI and the MISO. Okay, so the master toggles the clock, device change output data. Okay, so master and slave. The master toggles the clock again, and device they put the data into registers. Okay, and so this is what happens after the last bit. So basically you have this communication that's going on for all the bits, and then after the last bit we go to master end, and the communication unsets the slave select line, or rather it sets it to be 1 as opposed to 0. Okay, so in general, the devices, both devices, the master and the slave, need to know exactly how many bits are going to be transmitted. Okay, and then the master is going to pull the slave select line back high to turn off the communication. So that's the kind of thing that happens. So the slave could be sending data, and the master can say, oh, that's enough, it stops. And it just sets the slave select line up, and the communication stops. Okay, so there needs to be some coordination between the master and slave so that the communication makes sense. Okay, so that's part of the overall protocol. The I2C bus is an industry standard protocol for communication between local devices. So another thing, it's also a master-slave protocol. It's sometimes called the two-wire interface, and it sends byte-oriented messages. Okay, so the slave address is embedded in the message. Okay, so for the two-wire interface, you can have, so here are the two wires, SDA and SCL, and all of the devices can be connected to those two lines simultaneously. Okay, so unlike the slave select with the SPI communication, where each device has its own slave select line, these all share the data. So theoretically, all of these guys could read the data off the signal bus. Okay, so here's the clock. So this clocks the data, and this is the data. All of the devices could read the data. So what happens is, when the communication starts, is the data that's sent has the address of the device it's trying to communicate, and that's the first thing that's sent. So then the device knows, oh, they're talking to me. The other devices know, oh, they're not talking to me. And it kind of turns itself off, or kind of ignores it. But all the devices theoretically could be listening. So it's not like secure communication. But anyway, so you have the microcontroller master, and then you have the different slaves. So here's some different kinds of slaves. So there are basically, it says it's two-wire, but actually it's three-wire, because there's actually power associated with this. But everything has power, so that's not a big deal. That's not a communication thing. There are pull-up resistors. And so basically, the clock basically is pulling down, and the master sets the clock. It's basically pulling down, and every time it pulls down, then it pulls up. It's communicating when the next data bit can go. And the SDA again, because you have pull-up resistors, it's communicating by pulling down, by shorting or grounding the line, and that's how the bits are set. Okay, so each of these devices doesn't have to have a pull-up resistor. There are the bus itself, the communication bus, has the pull-up resistors. So here are some examples of devices that could use either the SPI or I2C communication. You've seen some in the labs. For example, the Gravitech Shield uses the I2C communication. And so there you saw explicitly you had this, each device, you know, the thermometer has one address, the 7-segment LED bank has its own address, and so forth. They each has its own address, so you send it the address, and then you can communicate with the device. Okay, so that's important. Here are just some examples of there are lots and lots of communication devices available. The last thing I want to talk about is the universal synchronous asynchronous receiver transmitter. It's a serial communication. Again, full duplex, that's the receiver and transmitter. Full duplex means it can communicate both ways simultaneously. In general, there's a high resolution baud rate generator. So the USART is what's used when we work with the serial monitor. The serial monitor then uses this to communicate. So again, this can provide serial terminal interface. That's exactly what the serial monitor does, it's that serial terminal interface that we work with. So, wow, that was fairly complex, this whole matter of the ATMEGA328. There's a lot of stuff going on here. This has been a crash course in the ATMEGA328. You can see there are lots of details, and we've just barely scratched the surface of all this. So you can see there's a lot more that we're going to be learning as we go through here. There's a lot of stuff about the clocks. There's a lot of stuff about interrupts. There's a lot of stuff about working with the alternate functions of the ports. We're going to be getting into all that. So this is just the overview so that you know what's coming. You have an idea of what's coming. And so we'll be digging into this further as we go along. Thanks for watching.